Hi all, welcome back to the lecture on the course Refrigeration and Air Conditioning. In the first part, we have studied the basic concepts and methods of refrigeration in a glance. In this part, we will discuss the first method of artificial refrigeration, that is the gas cycle refrigeration deeply. Like every other cycles, here also we made some assumptions to simplify the analysis of the cycle. The first assumption is the working fluid is a fixed mass of air that behaves as an ideal gas. This is the reason why it is also called air cycle refrigeration, because the air behaves as an ideal gas. The cycle is assumed to be a closed loop cycle. That is the second assumption. And the third one is all the processes within the cycle are reversible. There is no irreversibility. All the processes are reversible. And the last assumption is the specific heat of air remains constant throughout the cycle. There is no variation of specific heat with temperature. S1 equal to S2. The entropy of points 1 and 2 is same, and entropy of point 3 and 4 are same. So we can TH minus TL into S1 minus S4. So you can cancel these two terms. Finally you will get COP of a Carnot refrigerator is TL divided by TH minus TL. So it is clear that the COP of a Carnot refrigerator depends only on the working temperatures. Same way you can find the COP of a Carnot heat pump, which is equal to TH divided by TH minus TL, where QH is the desired output. So Carnot's cycle, reversed Carnot cycle, is an ideal cycle for constant temperature heat source and sink. So all the processes in a reversed Carnot cycle are completely reversible. So the cycle itself is a completely reversible cycle. As from the expression in the previous slide, we can say that the COP is a function of high and low temperatures only. So the applications of air refrigeration are aircraft cooling and liquefaction of gases. This is the application of air cycle refrigeration. But this reversed Carnot cycle has some limitations. The first limitation is the isothermal compression, that is the isothermal heat rejection process, and the isothermal expansion, that is the isothermal heat absorption process, are difficult to achieve in practice. Also, in this cycle, you have small volumetric refrigeration capacity and also have high volumetric flow rates of air. Because of these limitations, we introduce another cycle which is called ideal reversed Brayton cycle, which is also called Joule cycle or Bell-Coleman cycle. In this cycle, as you can see from the flow diagram, we have replaced two isothermal processes, that is isothermal heat rejection process at a high temperature and isothermal heat absorption process at a low temperature, is replaced with the isobaric processes, constant pressure heat rejection and constant pressure heat absorption processes, by replacing the compressor and the turbine with the heat exchangers. Here this is the high temperature heat exchanger and this is the low temperature heat exchanger. The other two processes are same. We are using a compressor and turbine to compress the air from 1 to 2. In this process, this is isentropic compression process. Isentropic compression process. In that process, the air gets the pressure increases, pressure and temperature increases. Then it is passed through the heat exchanger, which is an isobaric heat rejection process, reversible isobaric heat rejection process. So the air temperature decreases but the pressure is constant. Then from the state 3, the air is expands through the turbine, which is the reversible adiabatic or isentropic expansion process. So the air gets cooled, its temperature and pressure decreases. So that low temperature, low pressure air is then passed through another heat exchanger. So that process is a reversible isobaric heat absorption process. So through that heat exchanger, the air absorbs heat from the space where we need to maintain a cool atmosphere. You can see from this expression, you can take T1 and T2 outside of the bracket. You will get the expression T1 by T2 minus T1. So from this graph, COP versus the compression ratio, pressure ratio, you can see that if the pressure ratio increases, the COP of the Bell-Coleman cycle decreases. So if the processes are not, the compression and expansion processes are not isentropic, if it is polytropic process, then the COP of the Bell-Coleman cycle will be equal to mCp into T1 minus T4, which is the heat absorption process or refrigeration effect, divided by mCp n by n minus 1 gamma minus 1 by gamma T2 minus T1 minus T3 minus T4. As we know that the COP is refrigeration effect divided by work done for a polytropic process. The net work is the two compression isentropic compression work minus isentropic expansion work. So W net is equal to n by n minus 1 P2 minus P1 minus P1 P2 V2 minus P1 V1. So that is equal to, we can write, we know that PV is equal to MRT. So we can rewritten this equation as MR T2 minus T1 multiplied with n by n minus 1, where we can express this characteristic constant, gas constant for air R in terms of specific heat ratio gamma and Cp, that is R is equal to gamma minus 1 by gamma multiplied with the Cp. So by substituting all these terms, we can represent the work term as mCp n by n minus 1 gamma minus 1 by gamma. So Cp into gamma minus 1 by gamma is R, and n by n minus 1 is the term, and m is the mass flow rate. Within bracket T2 minus T1 minus T3 minus T4. This is the polytropic. If the compression and expansion processes are polytropic, this is the expression for COP of a Bell-Coleman cycle. For a fixed heat rejection temperature T3, that is this temperature, and a fixed refrigeration temperature T1, that is this temperature, you can see a Carnot cycle in the TS diagram 1, 2 dash, 3, 4 dash, and also you can see a reversed Brayton cycle or Bell-Coleman cycle 1, 2, 3, 4. So from this picture and from these expressions, you can see that the COP of a reversed Brayton cycle is always lower than the COP of a reversed Carnot cycle. See, a COP of a reversed Brayton cycle is equal to T1 divided by T3 minus T4, or you can use another expression, T1 divided by T2 minus T1. T2 minus T1. So this expression, from this expression you can easily understood that the COP of a Carnot cycle is always higher than that of a reversed Brayton cycle, because you can see T3 minus T1, this is the term in the denominator, this is the term in the denominator of the Brayton cycle T2 minus T1. So this term is higher than that of this term. So always COP of a Brayton cycle is less than that of the COP of a Carnot cycle. See this figure, after expansion the air state is this point 4 dash. So the expansion, because of this non-isentropic expansion, the refrigeration effect also decreases. As a result, the COP of actual reverse Brayton cycle will be considerably lower than the ideal cycles, because of the decrease in refrigeration effect and the increase in net work input. A design of efficient compressors and turbines plays a major role in improving the COP of the system. There are basically two types of air refrigeration systems, which are open system and closed system. In open system, there is no cold heat exchanger or low temperature heat exchanger. The cold air at the exit of the turbine after expansion flows into a room or cabin, and it is freely moves out to the atmosphere. We will take fresh air for the next cycle. In such a case, the low side pressure will be atmospheric. In open system, the low side pressure is atmospheric. There is no low side heat exchange process. Okay. There is no heat absorption process in an open cycle. This cycle is used in the aircraft refrigeration. Now, the other one is closed system. The same gas or air is flows through the cycle. We are not taking fresh air for each cycle. We will reuse the air again and again. Low side pressure can be above atmospheric. In this type of system, low side pressure can be above atmospheric. And these systems are known as dense air systems. A closed cycle air refrigeration system is called dense air systems. So here we have a low side heat exchanger. So the gas is here in these systems we can use gases other than air. For example, helium. So this lecture covers all the basics of air refrigeration system, the ideal cycle, and also the actual Brayton cycle for air refrigeration. Thank you.